Okay, for number 3, it says a particle moves along the x-axis so that its velocity at time t between 0 and 5 is given by that function. Velocity equals natural log of t squared minus 3t plus 3. The particle is at a position of x equals 8 at t equals 0. Part A, it says find the acceleration of the particle at time t equals 4. That should be pretty simple. The acceleration function is the derivative of velocity, so we have to take the derivative of velocity. So a prime of t, we're going to use the chain rule here. So the derivative of natural log is 1 over whatever we're taking the natural log of, so 1 over t squared minus 3t plus 3, and then times the derivative of the inside of the function, which would then be 2t minus 3. Be careful that is in parentheses. If it's not in parentheses, you're going to have an issue because you're going to want to multiply the 2t on top here and then leave the minus 3 outside. You've got to have that in parentheses. So just to simplify that a little bit, a of t, not a prime of t, that would have been v prime of t equals that. So a of t equals 2t minus 3 over t squared minus 3t plus 3. Now it says, what is the acceleration when t equals 4? So we just have to plug in 4 to the t values. So we get 2 times 4 minus 3 over 4 squared minus 3 times 4 plus 3. And then we simplify that expression from there. So a of 4 is equal to 2 times 4 is 8, minus 3 is 5, over 4 squared is 16, 3 times 4, so negative 12 plus 3. And that's simply 5 over, 7. Is there units indicated in this problem? No. So our acceleration when t equals 4 is 5 over 7. And that is our answer for part A. Notice it's worth 1 point, so you got to be able to take the derivative correctly and get the correct answer. So number 3, and this is part A. Okay. Part B says find all times in the interval 0 to 5 at which the particle changes direction. Well, a particle changes direction. If it's heading left or heading in the negative direction, it changes direction when its velocity changes from negative to positive. And if it's heading right, it's when its velocity changes from positive to negative. But the bottom line is, it changes direction when velocity changes signs. We were given the velocity function, so we're going to look at that. So v of t, I'm just going to rewrite this real fast, natural log of t squared minus 3t plus 3. Now, we are looking for when velocity changes signs. The only place that velocity can change signs is when velocity is equal to 0 or when velocity does not exist. Well, natural log does not exist when t is 0 or less, but that's outside of our domain anyways. So there's no place where velocity does not exist within the domain that we're given. So we're looking for when velocity is equal to 0. So 0 equals the natural log of t squared minus 3t plus 3. Okay. This is a calculator-based problem, but you honestly shouldn't need a calculator in order to solve this. I don't believe, but you can use a calculator. The key here is, though, you need to express v of t as 0 because you're looking for that value first of all. If you rewrite this as an exponential function, we would say something like this. We would say e, natural log has a base of e, so we'd say e to the 0 equals t squared minus 3t plus 3. And then e to the 0 is just 1, so 1 equals t squared minus 3t plus 3. And then we're going to solve for 0 here to get t. So t squared minus 3t plus 2 because we subtracted 1. And then we can factor this, so it'll be 0 equals t minus 2 times t minus 1. And so our values, our critical points, are when t equals 2 and t equals 1, both of which are within the domain that we're given. So we are looking for when velocity changes signs, so we have to look at our number line. 0 and 5 are our endpoints. We do not have to consider those because they're outside the domain. It was an open interval. But we do have to consider 1 and 2. This is when velocity is 0. So v of t is 0 at 1 and 2. And these are endpoints. We don't even have to indicate them. And we're going to just pick numbers to plug in between these values in order to figure out the signs. This is where your calculator would be helpful. So if you type in your velocity function into your calculator, you're going to type in natural log of x squared minus 3x plus 3. And then you change your window so that your x minimum is 0 and your x maximum is 5, because that's what we're concerned with here. And then we go ahead and graph it. We'll notice that the graph does something along this line. It starts here, and then it kind of does this, and then it goes back up like that. Okay? If we find our zeros, and it would probably be a good idea to do so, if we find our zeros by pushing F5 and lower bound, upper bound business, okay, we actually confirmed that this 0 is a 1, and then finding the other one, this 0 would be a 2. So again, we did that analytically. Since it's a calculator-based problem, you don't have to do it analytically. You could just type this into your calculator, into the Y list, and then find the zeros, and you should get 1 and 2. But what is convenient for the calculator more so is to figure out the signs of the velocity function. So if you look at the calculator, you would notice that the velocity function is positive between 0 and 1. It's above the x-axis. And then it's negative between 1 and 2. And it's positive between 2 and 5. So we are looking for when velocity changes signs. Well, we know velocity changes signs at 1 and at 2. So we would say the particle changes direction when t equals 1 and t equals 2, since v of t, velocity, changes signs at these points, at these times. And that is our answer there. Okay? So this part is worth 3 points. You're going to get 1 point for showing v of t equal to 0. You're going to get, I believe, 1 point for finding the critical points, and then 1 point for the answer, t equals 1 and t equals 2, with the justification that v of t must change signs. If you just say when t equals 1 and t equals 2 without checking a sign change or without the justification, you're not going to get that third point. And you're not going to get points just for a number line. The justification is not the number line. The justification is the words. All right, so for part C, it says, is the speed of the particle increasing or decreasing at t equals 4? The speed is increasing when velocity and acceleration have the same signs. And just a visual of that, if velocity is negative, that means we're heading in this direction. Okay? In order for us to speed up, we need something to push us. We need something to propel us to go faster. So if velocity is negative, acceleration is that force that pushes us. So if velocity and acceleration are both negative, we're speeding up. If velocity is negative and acceleration is positive, then acceleration is working against us, and therefore we're slowing down. Same thing the other way. If velocity is positive and acceleration is positive, it's pushing me along in the same direction, so I'm speeding up. If velocity is positive and acceleration is negative, acceleration is pushing or holding me back, so I'm slowing down. So the question is, when is the particle speeding up, or when is the speed increasing and decreasing? So we have to compare velocity and acceleration, and it wants to know at specifically t equals 4. So let me erase part B. Part A is going to come in handy because part A already gave us the acceleration at t equals 4, so that's nice. Part C wants to know whether we're speeding up or slowing down. So we have to evaluate v of 4. Well, it was given, v is given, so we're just going to plug that in. The natural log of 4 squared minus 3 times 4 plus 3. And you can use your calculator just to evaluate the function that you have in your y list already at t equals 4. You can do that. I'm going to simplify this a little bit, do it analytically. So that would be 16 minus 12 is 4 plus 3 is 7. So the question is the natural log of 7 a positive or a negative value? Well, if we rewrite this exponent, it would be e to what power? E to what power equals 7? Well, this would have to be a positive value in order for an exponential function to be 7. So we could say v of 4 is greater than 0. And we also know that a of 4 from part A is also greater than 0. So we would say the particle is speeding up. Let me use their words. The speed of the particle is increasing when t equals 4, since velocity of 4 and acceleration at 4 have the same sign. And it's not wrong if you say they're both positive, but it's not absolutely descriptive, because if you say velocity and acceleration are both positive, then the reader might assume that they must both be positive, and therefore exclude the other option of both being negative. So it's better to just say that they have the same sign, and we see that because they're both positive. This problem's worth 2 points. You're going to get a point for explaining that the speed of the particle is increasing, and then you're going to get the other point for the justification, showing that v of 4 and a of 4 are both positive, and then saying that they're the same sign.